For as long as humanity has existed, we have lived with the quiet assumption that tomorrow will resemble today. The sun will rise, the seasons will return. The world will remain familiar, yet the universe does not promise stability. It never has. Earth is a fragile island suspended in a vast and unpredictable cosmos, shaped by forces far older and far more powerful than our species. Scientists have spent decades studying these forces, mapping the risks that could reshape our future, and identifying the events that could alter life on Earth in ways we can barely imagine. Some of these threats are slow and familiar, unfolding in real time as our climate shifts and ecosystems strain. Others are sudden, violent, and rare, emerging from deep beneath the surface or from the silent darkness of space. A few are born from our own inventions, systems so complex that even their creators struggle to control them. And beyond all of this lie the cosmic events we cannot predict, phenomena that remind us how little we truly understand about the universe that surrounds us. This is not a story of fear. It is a story of perspective, a reminder that our world is temporary, dynamic, and deeply interconnected with forces far beyond human influence. By exploring the 7 most likely futures of Earth, we gain not only knowledge, but clarity. We learn what threatens us, what shapes us, and what it means to exist on a planet that is constantly changing. This journey begins with understanding, and once you hear these possibilities, it becomes impossible to see the world the same way again. Part 1. The collapse of Earth's climate system. Earth's climate system is a dynamic and interconnected structure that has remained relatively stable for thousands of years, allowing human civilization to develop and flourish. Today, this stability is weakening. The rate of environmental change has accelerated beyond anything recorded in human history. Scientists describe this shift not as a single event, but as a long-term destabilization driven by multiple reinforcing factors. This process is gradual, complex, and deeply rooted in the physics of the planet. The climate system consists of the atmosphere, the oceans, the cryosphere, and the biosphere. Each of these components influences the others. When one begins to change, the effects propagate throughout the entire system. Rising global temperatures alter atmospheric circulation. Warmer oceans expand and absorb less carbon dioxide. Melting ice sheets reduce the planet's ability to reflect sunlight. These changes create feedback loops that amplify the original disturbance. Over time, the system becomes increasingly unstable. One of the most significant concerns is the presence of climate tipping points. A tipping point is a threshold beyond which a system shifts into a new state that cannot be reversed on human timescales. Examples include the melting of the Greenland ice sheet, the collapse of the West Antarctic ice shelf, the dieback of the Amazon rainforest, and the thawing of permafrost that releases large quantities of methane. Once these processes begin, they accelerate independently of human influence. This makes them especially dangerous. The consequences of climate system collapse are not defined by sudden extinction. Instead, they manifest as long-term instability that affects every aspect of human life. Regions that are currently fertile may become too hot or too dry for agriculture. Coastal cities may face chronic flooding due to rising sea levels. Extreme weather events such as heat waves, storms, and droughts become more frequent and more severe. These disruptions place enormous pressure on infrastructure, economies, and social systems. Water scarcity is one of the most immediate risks. As temperatures rise, evaporation increases and rainfall patterns shift. Some regions may experience prolonged droughts, while others may face intense flooding. These changes affect food production, energy generation, and public health. In many parts of the world, water scarcity has already begun to influence migration patterns and geopolitical tensions. As the climate continues to change, these pressures are expected to intensify. Another critical factor is the weakening of large-scale atmospheric and oceanic circulation systems. The jet stream, which influences weather across the northern hemisphere, becomes less stable as temperature differences between the poles and the equator decrease. This can lead to prolonged periods of extreme weather, such as extended heat waves or severe cold spells. Similarly, changes in ocean currents can disrupt marine ecosystems and alter global climate patterns. These shifts have far-reaching consequences for both natural and human systems. The collapse of Earth's climate system is considered the most likely future scenario because it is already underway. The evidence is visible in rising global temperatures, shrinking glaciers, intensifying storms, and shifting ecosystems. These changes are not predictions. They are observations. The question is not whether the climate will continue to change, but how quickly and how severely these changes will unfold. Despite the seriousness of the situation, this scenario does not represent the end of humanity. It represents the end of the stable environmental conditions that supported the rise of civilization. The future will depend on how effectively societies adapt to new realities. Technological innovation, international cooperation, and scientific understanding will play crucial roles in determining the outcome. The challenge is immense, but not insurmountable. The collapse of Earth's climate system is a slow but powerful transformation. It is driven by physical processes that operate on global scales and long timescales. It reshapes coastlines, ecosystems, and human societies. It forces adaptation, migration, and innovation. It is the first and most probable path toward the end of Earth as we know it, not through sudden destruction, but through the gradual unraveling of the system that has sustained life for millions of years. Part 2. The supervolcano that darkens the world. A supervolcano eruption is one of the most powerful natural events known to science. Unlike ordinary volcanic eruptions, which can affect regions or continents, a supervolcano has the potential to influence the entire planet. These eruptions release enormous quantities of ash, sulfur dioxide, and volcanic gases into the atmosphere. The result is a long period of global cooling, reduced sunlight, and widespread ecological disruption. Scientists classify this scenario as less likely than climate system collapse, but still significant on geological timescales. A supervolcano is defined not by its shape, but by the size of its magma chamber and the scale of its eruptions. The most well-known example is the Yellowstone caldera in the United States. Other major systems include Toba in Indonesia, Taupo in New Zealand, and the Campi Flegrei complex in Italy. These systems have erupted in the distant past with catastrophic consequences for global climate and life on Earth. Their activity is monitored continuously, but predicting an eruption remains extremely difficult. When a supervolcano erupts, the immediate effects are devastating. The surrounding region experiences massive explosions, pyroclastic flows, and widespread destruction. However, the global consequences are driven by what enters the atmosphere. Ash particles and sulfur aerosols rise high into the stratosphere, where they can remain for years. These particles reflect sunlight back into space, reducing the amount of solar energy that reaches the surface. This phenomenon is known as volcanic winter. Volcanic winter leads to a rapid drop in global temperatures. Crops fail due to reduced sunlight and shorter growing seasons. Ecosystems struggle to adapt to sudden cooling. Ocean circulation patterns may shift as surface temperatures decline. Historical records show that even moderate volcanic eruptions, such as Mount Tambora in 1815, caused global famine and severe climate anomalies. A supervolcano would produce effects far greater in scale and duration. The ash cloud itself poses additional risks. Fine ash can travel thousands of kilometers, contaminating water supplies, damaging infrastructure, and disrupting transportation. Air travel becomes dangerous or impossible across large regions. Ash accumulation can collapse roofs, destroy machinery, and render farmland unusable for years. These impacts create long-term economic and social challenges that extend far beyond the eruption zone. One of the most concerning aspects of a supervolcano eruption is the unpredictability of recovery. Climate models suggest that global temperatures could remain depressed for a decade or longer. This prolonged cooling would place enormous pressure on food production, energy systems, and global trade. Societies would need to adapt to colder climates, reduced harvests, and persistent atmospheric haze. The psychological and cultural effects of a darkened world would also be significant. Despite the severity of this scenario, scientists emphasize that supervolcano eruptions are extremely rare. They occur on timescales of tens or hundreds of thousands of years. The likelihood of such an event occurring within a human lifetime is low. However, the consequences are so far-reaching that the scenario remains an important part of global risk assessments. Understanding these systems helps researchers develop early warning methods and resilience strategies. Modern technology provides tools for monitoring volcanic activity. Seismic sensors detect ground movement. Gas analyzers measure changes in volcanic emissions. Satellite imagery tracks surface deformation and thermal anomalies. These methods offer valuable insights, but they cannot predict the exact timing of an eruption. Supervolcanoes operate on geological timescales, and their behavior is influenced by complex processes deep within the Earth's crust. The supervolcano scenario is not the end of humanity. It is a profound disruption that challenges global stability. Human societies have survived volcanic winters in the past, though on a much smaller scale. The key difference today is the interconnected nature of the modern world. A major eruption would affect global supply chains, international relations, and technological systems. The impact would be felt everywhere, regardless of distance from the eruption site. This scenario represents the second most likely path toward the end of Earth as we know it. It is defined not by fire, but by darkness. A world where sunlight fades, temperatures fall, and ecosystems struggle to adapt. A reminder that the planet's interior holds forces capable of reshaping the surface in ways that transcend human control. The supervolcano that darkens the world is a rare but powerful example of Earth's ability to reset its own environment. Part 3. The day the asteroid arrives. An asteroid impact is one of the most dramatic natural events that can occur on Earth. Although large impacts are rare on human timescales, they are inevitable on geological scales. Earth has been struck many times in its history, and each major impact has left a permanent mark on the planet's surface and its ecosystems. Scientists study these events not because they expect one tomorrow, but because the consequences of a large impact are global and long-lasting. Asteroids vary greatly in size, composition, and trajectory. Most burn up in the atmosphere as harmless fireballs. Some reach the surface as small meteorites. Only a tiny fraction are large enough to cause regional or global damage. An asteroid several hundred meters wide could destroy a city or devastate an entire region. An asteroid several kilometers wide could alter the climate, disrupt food systems, and reshape life on Earth for decades. The most famous example is the Chicxulub impact, which contributed to the extinction of the dinosaurs 66 million years ago. Modern astronomy has identified and cataloged thousands of near-Earth objects. These objects are monitored continuously to determine their orbits and assess potential risks. Most known asteroids pose no threat. However, the challenge lies in detecting smaller objects that are still capable of causing significant damage. Some asteroids approach from directions that make them difficult to observe, such as from the direction of the Sun. This means that even with advanced technology, surprises are still possible. If a dangerous asteroid were discovered, the timeline would determine the response. With decades of warning, space agencies could attempt to alter its trajectory using kinetic impactors or gravitational tugs. These methods rely on small changes accumulating over long periods. With only a few years of warning, options become more limited. With months or weeks of warning, the focus shifts from deflection to emergency preparedness. The outcome depends heavily on how early the threat is detected. The moment an asteroid enters the atmosphere, the physics becomes unavoidable. A large object traveling at tens of kilometers per second releases enormous energy upon impact. The explosion can exceed the power of the largest nuclear weapons. Shockwaves flatten forests and cities. Heat ignites fires across vast areas. Debris is thrown high into the atmosphere, where it can block sunlight and trigger a period of global cooling. This phenomenon is known as impact winter. Impact winter disrupts climate patterns and reduces agricultural productivity. Crops fail due to lack of sunlight. Temperatures drop rapidly. Ecosystems struggle to adapt to sudden environmental stress. The severity of these effects depends on the size of the asteroid and the amount of material ejected into the atmosphere. Even a moderate impact could cause years of climatic instability. A larger impact could reshape the planet for generations. The oceans are not a safe target. An asteroid striking the ocean generates massive tsunamis that can travel across entire basins. Coastal regions, where much of the world's population lives, would be at extreme risk. Saltwater contamination, infrastructure damage, and long-term ecological disruption would follow. The global economy, which depends on coastal trade routes, would face severe challenges. Despite the dramatic nature of this scenario, scientists emphasize that large impacts are extremely rare. The probability of a civilization-ending asteroid strike within a human lifetime is low. However, the consequences are so severe that monitoring and preparedness remain essential. International cooperation plays a crucial role in tracking near-Earth objects and developing potential mitigation strategies. The ability to detect and respond to an asteroid threat is one of the few global challenges that truly requires a unified planetary effort. The day the asteroid arrives is not defined by fear, but by physics. It is a reminder that Earth moves through a dynamic and sometimes hazardous cosmic environment. It is also a reminder of the importance of scientific observation, technological innovation, and global coordination. While the likelihood of such an event is low, the impact would be profound. This scenario represents the third most likely path toward the end of Earth as we know it, a rare but inevitable event on geological timescales, shaped by forces far beyond human control. Part 4. The pandemic that reshapes humanity. A global pandemic is one of the few natural events capable of transforming human civilization within a single generation. Throughout history, infectious diseases have reshaped societies, economies, and cultures. Modern medicine has reduced many risks, but it has not eliminated the possibility of a large-scale biological event. Scientists consider this scenario moderately likely because it is driven by biological evolution, human behavior, and global interconnectedness. These factors create conditions in which new pathogens can emerge, spread, and adapt with remarkable speed. A pandemic begins when a pathogen acquires the ability to move efficiently between hosts. This can occur through mutation, recombination, or spillover from animals to humans. Many viruses circulate silently in wildlife populations. When ecological pressures increase, such as habitat loss or climate change, the probability of cross-species transmission rises. Once a pathogen enters the human population, its future depends on how well it replicates, how easily it spreads, and how effectively it evades the immune system. Modern transportation networks allow diseases to travel across continents within hours. A pathogen that once would have remained confined to a single region can now reach every major city in a matter of days. This rapid spread challenges public health systems and complicates containment efforts. Early detection is crucial, but not always possible. Some pathogens spread before symptoms appear. Others cause mild illness in many individuals, making them difficult to track. These characteristics allow outbreaks to grow unnoticed until they reach a critical threshold. The severity of a pandemic depends on several factors. These include the pathogen's transmissibility, its mortality rate, the duration of infectiousness, and the availability of medical countermeasures. A highly lethal pathogen may burn out quickly if it kills hosts before they can spread it. A moderately lethal pathogen with efficient transmission poses a greater long-term threat. Scientists also consider the potential for long-term health effects, which can strain healthcare systems and reduce workforce capacity for years. Human behavior plays a significant role in shaping pandemic outcomes. Population density, travel patterns, cultural practices, and economic pressures influence how quickly a disease spreads. Public trust in institutions affects compliance with health measures. Misinformation can undermine response efforts. Inequality can limit access to medical care and increase vulnerability in certain communities. These social factors interact with biological processes to determine the overall impact of a pandemic. Technological advances offer powerful tools for managing pandemics. Genomic sequencing allows scientists to identify pathogens quickly and track their evolution. Vaccines can be developed faster than ever before. Antiviral drugs and monoclonal antibodies provide additional layers of protection. However, these tools require global coordination, manufacturing capacity, and equitable distribution. Without these elements, even the best technologies cannot prevent widespread disruption. A major pandemic would affect more than public health. It would influence global trade, supply chains, and economic stability. Industries dependent on physical presence, such as transportation, tourism, and manufacturing, would face severe challenges. Education systems would need to adapt to remote or hybrid models. Governments would be forced to balance public safety with economic survival. These pressures could reshape political landscapes and alter international relations. The psychological impact of a pandemic is often underestimated. Prolonged uncertainty, social isolation, and fear of illness can affect mental health on a global scale. Communities may experience collective trauma. Cultural norms may shift as societies adapt to new realities. Some changes may be temporary. Others may become permanent features of human life. The long-term consequences extend far beyond the duration of the outbreak itself. Despite the challenges, pandemics also drive scientific progress. They accelerate research in immunology, virology, and biotechnology. They highlight weaknesses in global health systems and motivate reforms. They encourage international cooperation and data sharing. These advancements can reduce the severity of future outbreaks and improve resilience. Humanity has survived pandemics before, and each event has contributed to a deeper understanding of disease and adaptation. The pandemic that reshapes humanity is not defined by extinction. It is defined by transformation. It alters how societies function, how economies operate, and how individuals relate to one another. It exposes vulnerabilities but also reveals strengths. It forces innovation, adaptation, and reflection. This scenario represents the fourth most likely path toward the end of Earth as we know it, not through sudden collapse, but through a profound reconfiguration of human civilization driven by biological forces that evolve alongside us. Part 5. The technology that turns against its creators. The idea of technology turning against its creators is often portrayed through images of hostile robots or conscious machines. In scientific reality, the threat is far more subtle and far more plausible. It emerges not from rebellion, but from complexity. Modern technological systems are vast, interconnected, and increasingly autonomous. They operate at speeds and scales that exceed human oversight. When these systems fail, malfunction, or interact in unexpected ways, the consequences can be global. This scenario is considered moderately likely because it is rooted in the structure of modern civilization itself. Technology today forms the backbone of nearly every essential function. Power grids, communication networks, financial markets, transportation systems, and industrial infrastructure all depend on automated processes. These systems are efficient, but they are also fragile. A small error in one component can cascade across an entire network. This phenomenon is known as systemic risk. It occurs when the failure of one part triggers failures in others, creating a chain reaction that is difficult to stop. Artificial intelligence adds another layer of complexity. Modern algorithms can analyze data, make decisions, and optimize processes without direct human intervention. These systems are powerful, but they are also opaque. Their internal logic is often too complex for humans to fully understand. When an AI system makes an unexpected decision, it can be difficult to determine why. This lack of transparency becomes dangerous when AI is integrated into critical infrastructure, such as energy management, logistics, or defense systems. One of the most significant risks comes from misalignment. This occurs when a system follows its instructions too literally or optimizes for the wrong objective. A machine does not understand context, ethics, or long-term consequences. It simply executes its programming. If the programming is flawed, incomplete, or misinterpreted, the system may produce harmful outcomes even while functioning exactly as designed. This type of failure is not malicious. It is mechanical, but the effects can be severe. Cybersecurity is another major concern. As technology becomes more interconnected, the number of potential vulnerabilities increases. A single breach can compromise entire networks. Cyber attacks can disrupt power grids, shut down hospitals, manipulate financial markets, or disable communication systems. These attacks do not require advanced artificial intelligence. They require access, opportunity, and intent. The more dependent societies become on digital infrastructure, the more damaging these attacks can be. Automation also introduces economic and social risks. As machines replace human labor, entire industries may shift or disappear. This can lead to unemployment, inequality, and social unrest. While automation increases efficiency, it can also destabilize communities that rely on traditional forms of work. These disruptions may not be catastrophic on their own, but they contribute to broader instability. When combined with other technological failures, they can amplify the overall impact. Another dimension of this scenario involves the interaction between multiple systems. Modern infrastructure is deeply interconnected. Power grids depend on communication networks. Communication networks depend on data centers. Data centers depend on cooling systems and energy supplies. A failure in one system can quickly spread to others. This interdependence creates a situation where no single failure remains isolated. The entire technological ecosystem becomes vulnerable to cascading disruptions. The most extreme version of this scenario involves autonomous systems making decisions that humans cannot override. This could occur in military contexts, where automated defense systems react faster than human operators. It could occur in financial markets, where algorithmic trading triggers rapid fluctuations. It could occur in industrial settings, where automated machinery operates without sufficient safeguards. In each case, the danger arises not from intent, but from speed and complexity. Despite these risks, technology also provides tools for resilience. Redundant systems, improved cybersecurity, transparent AI models, and robust safety protocols can reduce the likelihood of catastrophic failure. International cooperation can help establish standards and prevent escalation. The challenge lies in implementing these measures before a major incident occurs. As systems grow more complex, the window for effective intervention becomes smaller. The technology that turns against its creators is not a story of rebellion. It is a story of dependence. It is the recognition that modern civilization relies on systems that are powerful, intricate, and sometimes unpredictable. When these systems fail, the consequences can be widespread. This scenario represents the fifth most likely path toward the end of Earth as we know it, not through conscious machines, but through the unintended consequences of the technologies that sustain modern life. Part 6. The Sun that Burns the Earth. The Sun is the source of all energy that sustains life on our planet. It drives climate, fuels ecosystems, and shapes the conditions that allow civilization to exist. Yet the same star that makes life possible will one day make it impossible. This scenario is not imminent. It unfolds over hundreds of millions of years. Scientists consider it inevitable, not because of speculation, but because it is rooted in well-understood stellar evolution. The Sun is a main sequence star, and like all stars of its type, it gradually becomes hotter and brighter as it ages. The Sun generates energy through nuclear fusion in its core. Over time, the composition of the core changes. Hydrogen is converted into helium, and the increasing concentration of helium raises the core's temperature. This process causes the Sun's luminosity to increase. Even a small rise in brightness has significant consequences for Earth. Climate models show that a 10% increase in solar output would trigger a runaway greenhouse effect. This would cause the oceans to evaporate and the atmosphere to become thick with water vapor. Such conditions would make the planet uninhabitable long before the Sun reaches its final stages. The timeline for this transformation is measured in geological epochs. Within 1 billion years, the Sun will be bright enough to destabilize Earth's climate permanently. The oceans will begin to retreat as evaporation outpaces rainfall. Water vapor, a powerful greenhouse gas, will trap more heat in the atmosphere. This feedback loop accelerates warming. Surface temperatures will rise to levels that prevent liquid water from existing. Life as we know it will disappear. Microbial life may persist for some time, but complex organisms will not survive the extreme heat. As the Sun continues to age, the changes become more dramatic. In several billion years, the Sun will exhaust the hydrogen in its core. It will then begin to fuse hydrogen in a shell surrounding the core. This process causes the outer layers of the Sun to expand. The Sun will enter the red giant phase. Its radius will increase hundreds of times. Mercury and Venus will be engulfed. Earth may also be consumed, depending on the details of orbital dynamics and mass loss. Even if Earth avoids direct engulfment, the intense heat will strip away the atmosphere and melt the surface. The red giant phase represents the most extreme stage of solar evolution. The Sun's outer layers will glow with a deep red hue. The solar wind will intensify, carrying away large amounts of material. This mass loss may cause Earth's orbit to expand slightly. However, the increase in distance will not be enough to protect the planet. Surface temperatures will exceed the melting point of rock. The oceans will have long since vanished. The atmosphere will be gone. Earth will become a scorched and barren world. Despite the inevitability of this scenario, it is not a threat to current or near-future generations. The timescales involved are vast. Humanity has millions of years to adapt, evolve, or leave the planet entirely. The scientific value of this scenario lies not in its immediacy, but in its demonstration of cosmic impermanence. It reminds us that Earth is not a permanent home. It is a temporary environment shaped by the life cycle of a star. The long-term future of humanity depends on technological and biological evolution. If civilization continues to advance, it may develop the ability to migrate to other worlds or build habitats independent of planetary surfaces. These possibilities remain speculative, but they illustrate the potential for life to persist beyond the lifespan of its original environment. The Sun's evolution is a natural process that cannot be stopped. The only question is whether life will adapt or disappear. The Sun that burns the Earth is not a sudden catastrophe. It is a slow transformation driven by the physics of stellar evolution. It unfolds over billions of years, reshaping the solar system and determining the ultimate fate of our planet. This scenario represents the sixth most likely path toward the end of Earth as we know it. It is inevitable, but distant. It is a reminder that even the most stable and familiar forces in our universe are temporary. The Sun gives life, and one day it will take it away. Part 7. The cosmic events we cannot predict. The universe is filled with forces that operate far beyond the scale of human experience. Some of these forces are well understood, such as the life cycles of stars or the motion of galaxies. Others remain unpredictable, rare, and deeply mysterious. Scientists classify these events as low probability but high impact. They are difficult to anticipate because they originate from distant regions of space, evolve rapidly, or involve physical processes that are not yet fully understood. These cosmic events represent the most uncertain path toward the end of Earth as we know it. One of the most dramatic examples is the gamma-ray burst. A gamma-ray burst is an intense flash of high-energy radiation produced by the collapse of a massive star or the merger of neutron stars. These bursts can release more energy in a few seconds than the Sun will emit in its entire lifetime. If a gamma-ray burst were to occur within our galactic neighborhood and be directed toward Earth, it could strip away the ozone layer and expose the surface to harmful ultraviolet radiation. This would disrupt ecosystems and potentially trigger mass extinctions. Fortunately, gamma-ray bursts are extremely rare and usually occur in distant galaxies. Another unpredictable threat comes from rogue objects. Rogue planets, brown dwarfs, or even small black holes can drift through the galaxy without orbiting a star. These objects are difficult to detect because they emit little or no light. If a rogue object were to pass through the solar system, it could disturb planetary orbits, alter the trajectory of comets, or disrupt the stability of the outer planets. Even a slight gravitational influence could send long-period comets toward the inner solar system, increasing the risk of impacts. The probability of such an encounter is low, but not zero. Black holes represent another category of cosmic uncertainty. A black hole does not need to collide with Earth to cause damage. Its gravitational field can distort space around it, affecting the orbits of nearby objects. A small black hole passing through the solar system could disrupt the delicate balance that keeps planets in stable orbits. Although astronomers monitor the sky for massive objects, smaller black holes are nearly invisible. Their presence can only be inferred through gravitational effects, which makes early detection challenging. Solar phenomena also contribute to cosmic unpredictability. While the Sun follows a regular cycle of activity, extreme solar flares or coronal mass ejections can occur without warning. These events release charged particles that can damage satellites, disrupt communication systems, and overload power grids. A sufficiently large solar storm could cause widespread technological failure. Historical records show that such events have occurred in the past. The most famous example is the Carrington event of 1859. A similar event today would have far greater consequences due to global dependence on electronic infrastructure. Cosmic radiation is another factor that influences life on Earth. High-energy particles from distant astrophysical sources constantly bombard the planet. Earth's magnetic field and atmosphere provide protection, but these shields are not perfect. Variations in cosmic radiation can affect climate, biological evolution, and technological systems. Although these variations are usually small, extreme events could have noticeable effects. Scientists continue to study the relationship between cosmic radiation and Earth's environment, but many aspects remain uncertain. The expansion of the universe introduces additional unknowns. Dark matter and dark energy make up most of the universe's mass and energy, yet their nature is still not fully understood. These components influence the motion of galaxies and the large-scale structure of the cosmos. Changes in the distribution of dark matter or fluctuations in dark energy could theoretically alter cosmic dynamics in ways that are difficult to predict. While these possibilities are speculative, they highlight the limits of current scientific knowledge. Despite the uncertainty surrounding these cosmic events, it is important to recognize that they are rare. The vastness of space makes direct encounters unlikely. However, the potential consequences are significant enough to warrant scientific attention. Astronomers use advanced telescopes, gravitational wave detectors, and particle observatories to monitor the universe for signs of unusual activity. These tools provide valuable data, but they cannot eliminate uncertainty entirely. The universe remains a place of immense complexity and unpredictability. The cosmic events we cannot predict represent the seventh and least likely path toward the end of Earth as we know it. They remind us that our planet exists within a dynamic and sometimes hazardous cosmic environment. They also highlight the importance of scientific exploration and observation. Understanding the universe is not only a pursuit of knowledge, it is a way to prepare for the unknown. These events may be unlikely, but they illustrate the profound connection between Earth and the cosmos that surrounds it. In the end, every scenario we explored leads to the same realization. Earth is not a fixed or permanent world. It is a living system shaped by forces far larger than us. From the shifting climate beneath our feet to the silent energies moving through the universe, understanding these possibilities does not make the future darker. It makes it clearer. It reminds us that knowledge is our greatest tool and that awareness is the first step toward resilience. If this journey gave you a new perspective, if it made you think differently about our planet and our place in the cosmos, consider supporting this project. Like the video, share it with someone who would appreciate the story, and subscribe for more documentary explorations. Your support helps these ideas reach further and keeps the journey moving forward.